As we've been talking about rotation, it has analogs with translational motion. So an object that goes from here to there, it has position x, velocity v, acceleration a, and for rotation we use rotational position theta, angular speed or rotational speed omega, and angular acceleration alpha. And so we're kind of like they're analogous. We're kind of replacing these variables with its rotational counterpart. Um, For an object that's moving from here to there, its inertia is measured by mass. And for rotational inertia, it's the letter I, right? Which is the formulas that we looked at, a calculation that we have to do. We just finished with torque, which is the analog of force. Like torque is like a twisting force. And yeah, there's more analogs with translational motion here. So today, the big one is Newton's second law for um, rotational motion. So we replace force with torque, mass is rotational inertia, and acceleration is angular acceleration alpha. Now, a couple of months ago, we used kinetic energy, mv squared over 2 for some object moving. That's that's translating, and so we put the subscript here, tr, for translational. And rotational motion also has an analog to this, which is rotational kinetic energy. Instead of mv squared, it's rotational inertia times angular speed squared over 2. And eventually we'll get to momentum for rotational motion. This is called angular momentum, which is, again, mass times v. This would be rotational inertia times omega. We'll focus on those later. And today, the kind of the big one we're using is this one. So we're going to jump straight into an example. We have a disk, okay, mass, radius. It's initially at rest. And on the top of this disk, or you can say around this, we have a rope, and we have a little bit of the rope extending here. And so when we pull on this, because we're going to pull on this, and this thing will start rotating around its center of axis here, the middle of the disk. Um, It'll, of course, start to rotate in this direction. Now we're going to pull on this rope and give it a tension 18 newtons. And then we have some questions here. What is alpha? What is the acceleration of the rope? And what is omega? So first thing we should do is draw a free body diagram. Here it is. We'll put a force on this Ft in that direction. So part A, oh, excuse me, this is more of like a torque diagram. Um, yeah, this is a torque diagram because the disk has mass m, and we don't really care about the gravitational force of the disk. For this case, we just care about the torque. And the only force that's causing torque on this thing is from the rope, which is putting a tension force that way. So anyway, let's go ahead and begin. The sum of torque, the sum of all torque is equal to, so I was going to write R times F. This is I times alpha, rotational inertia times angular acceleration. Now I'm going to label R on this diagram, which is simply just the radius. And so the only torque here is R times F T equals the rotational inertia of a disk, which is mr r squared over 2 times alpha. Now, this is our first time through this, so we could do things algebraically. I think right now we'll just plug in some numbers and figure out what alpha is. We know r, we know m, and we know ft, which is everything here. I can I can cross off an r, right? I can cancel an r on both sides. But actually, later on, it's going to be useful that we keep that r there. And so I'm going to keep it. And so we'll put in zero point 0.4. We'll put in 18. Okay, the mass is 3 squared, don't forget that, over 2 times alpha. And I'll tell you right now why it's good to keep that r there, because later on, if I need to know what I equals, if I need to know what this quantity is, well, it's kind of like in my math right here. If I got rid of that r, I wouldn't really know what this is. I'd have to multiply an r times. It would just make it tedious. So um, for the time being, I'm not going to cancel that r. This is 7.2. And then we have 3 over 2.24 times alpha. We'll just divide 0.24. This comes out to 30 radians per second squared is alpha. Now we could have also done, we could have also rearranged this. For example, if there's no numbers involved, we could have rearranged this to m, something like this. I'm not showing my steps here, but we could have rearranged this for alpha. And then here, of course, we can cancel the r. Just wanted to show that. Okay, that's part A. Part B, what is the acceleration of the rope? So as we pull this rope with a constant force, or, imagine I'm pulling this with yeah, like a constant force of 18 newtons. This part of the rope is accelerating with acceleration A, and this rope is not stretchy. This is also acceleration A, so all points along the rope are moving at the same acceleration, including a point right here, which is moving with this acceleration. If you guys remember, this is tangential acceleration, and we have an equation for this, which is AT is equal to R alpha. But I'm just going to write A is equal to R alpha. And so A is equal to the radius, which is zero point 0.4, times alpha, which is 30, which is 12. Whenever we have alpha that's radians per second squared, accelerations are meters per second squared. Just plain old acceleration, centripetal acceleration or whatever. Okay, and then finally part C, what is omega? What is the angular speed of this thing after 4 seconds? And we could make a list, we could make our kinematics list. And since I'm already done doing it, we'll just continue from there. So 0, it initially started at rest. We want to know what is omega. This is 12 radians per second squared, and this would be after 4 seconds. And of course, we can use this. 0, 12 times 4. Rush through that. Looks good to me, though. let's keep going. Okay, great. So here what we have is it's a rigid surface here, like a ceiling, and there's two beams coming down, basically holding a rod that is free to rotate about point P. So right now it's being held by a thread, but if I cut the thread, what's going to happen is that rod, which is here, is going to start to rotate. And so I get a little fancy. I probably shouldn't, but yeah, it's going to rotate. So no, this is not a great picture of it, but it's going to rotate until it goes vertical. Now, I suppose what I could do is do that here. At some point, it will be about here. Oops. And at some point, it might have just been easier if I just drew this again. So does that make sense? Initially, it's held here with a thread, but once you cut the thread, it will start to fall this way until it's vertical, but really it'll act kind of like a pendulum. It'll swing back and forth, you know, for some time. I'm actually going to keep this diagram because this will be useful later. So just move that there. So we have a rod, mass M, length L. Yeah, free to pivot around point P. We're going to cut the thread. And so question A is, what is the angular acceleration? First, let's draw a free body diagram for the rod. And the rod has a gravitational force, mg, acting at the center of mass. Now, sorry, I'm already assuming that I've cut the thread, so the thread is gone. Okay. And now this thing will begin ex- uh, to rotate, and it will have some angular acceleration like this. Okay. Now, if this is a true free body diagram, which that's what we do, there's also a force P. You can say it's like a force FP. But because that's where the axis of rotation is, then of course there's no torque from this force, which is not contributing to its angular acceleration. So the sum of all torque is I alpha. Like I just said, this torque does not matter. There is no torque because RP is 0. And so the only torque is from the gravitational force. Still don't know what to call this. I've been calling it RC. And let's put in our torque. This is RC, or you can just call it R. There's only one times mg. The rotational inertia for a rod is ml squared over 3 times alpha. As we did before, I'm going to leave it like this because what if we want to know later what is I equal to? Well, we're going to do the work here and keep it. Now R is L over 2, right, which is 2. Mg is 15, and M is 1.5. L is 4 squared times alpha. So this is 30. Let's see. 4 squared 16 times 1.5 divided by 3 is 8. 30 over 8. 3.75 radians per second squared. Okay, now, yeah, I just realized I don't need this one for this one, but I will keep it for another video. We want to know what is the acceleration at point A and what is the acceleration at point B. At point A, there is a tangential acceleration, but we'll call it AA. And at point B, there is also a tangential acceleration. We'll call it AB, which of course we've done many times before. And so we'll just calculate those. I think I'll just do them here. AA is equal to RA times alpha. What is the distance from A? So remember, R is the distance from there to there. This is RA, which is half the length, which is 2. 2 times 3.75, which is 7.5 meters per second squared. Now, what do you all think? Is the tangential acceleration at point B, is that the same as A? Because this thing is falling. Let's see. This is RB times alpha. RB, and this is where my diagrams get real messy. This is RB, which is the length, which is 4. It's the length times alpha, which is 4. Oops. And alpha was 3.75, which is just twice this, right? Which is 15 meters per second squared, which I still think is um, really interesting. That, okay, you have this, which I've drawn all over, you have this rod. Okay, so you have this rod here, and let's not do that. I don't know, just you just have an object next to it, you drop them at the same time. You have like a baseball or something. And initially, anyway, the rod falls away faster than the baseball. The baseball will fall, it's in free fall, it'll fall at 10 meters per second squared downward. Um, and the end of the rod will fall away at a faster rate, 15 meters per second squared, at least initially. Um, yeah, I just think that's really interesting. But whereas point A though is less than the acceleration of gravity. So if you had an object sitting on this rod and you drop this thing, um, the object will kind of stay on the rod for a bit until it just fell off. If you had something sitting at point B though, and you dropped this thing, you held it in place and then you dropped it, the rod would move away and leave that object behind. Cool. And I think that was it.